In this video, we will continue discussing the dihedral group. We'll give a slightly different way to look at the reflections and rotations that will actually allow us to describe the group and the relations between the different elements and actually prove that it is a subgroup of the symmetric group. Of course, you have to ask yourself eventually, is there a better way to express these formulas for arbitrarily large n? I mean, if I set n equal to 100, I certainly don't want to write down 100 numbers on a cycle. That would take forever, particularly for the purposes of writing proofs. I mean, in order to prove that this forms a subgroup, we need a better way to write down the bijections. And so it turns out there is a better way. Assuming you've labeled your vertices clockwise starting at 0, you can use modular arithmetic. Namely, what does this rotation map actually correspond to? It corresponds to adding 1 mod n. You go to the right by adding 1 until you're at the end. When you add 1 to 5, you get 6, which mod 6 is congruent to 0. And so this is true in general. The rotation map is supposed to be this one. But n minus 1 plus 1 is n, which is congruent to 0 mod n. So you can see that this definition is the same as this one. And the advantage of that is that this gives a formula. And why do I care about that? Because then computing kth powers of the rotation operation are easy. What is the kth power? Well, if you're just adding 1 for the first power, adding 2 r squared then, that's just r of I plus 1 mod n, right? But that's just I plus 1 mod n, which is I plus 2 mod n. This is the exact same idea as skip counting by 2. And you can see this idea in general. For arbitrary k, you're just skip counting by k. You're just adding 1k times. And this modulus just says that if you ever go past the end of the cycle, you loop back around to the beginning. For the rotations, this formula is not really that useful, but it turns out we can find a nice formula for all the reflections that is of a similar format. And that's what we're going to talk about next. Namely, I mean, if you view this as lying on the x-axis in the plane, what are you really doing? You're just negating the y-coordinate. That makes sense to just say it looks like you're negating. So let's think about that. What happens if you just negate a vertex? Well, 0 goes to 0, 1 goes to negative 1, but what is negative 1 mod 6? It's the same thing as 5. Similarly, negative 2 mod 6 is 4. And so you see that I actually do send 2 to its negative and vice versa. Each one of these elements in this original cycle is actually paired with its additive inverse with respect to modular arithmetic. And if you never like this formula, you could also just put n mod x mod n, and this actually guarantees that whatever you get here is actually correct, right? So 1 goes to 6 minus 1, that is 5. 5 goes to 6 minus 5, that is 1. You do actually see that you do get a bijection. I mean an involution. But I tend to find this formula a little easier to work with for calculation purposes, for theory, but for explicit calculations, this one's a little easier. You see this works with the odd case as well. The additive inverse of 1 mod 3 is 2, because 1 plus 2 is 3. So 1 gets sent to 2, 2 gets sent to 1. So we have this negation operation. When you do a double negative, you do in fact get the identity. And so it has the right property, and so it does correspond to this reflection. Why do I care about that? Well, because let's see what happens when you do k rotations in a reflection. Note, when I had us fill out the tables earlier in the semester, depending on the semester, I might have had us do things a little backwards. Because I might, depending on, there's always a debate about what R times S should mean when you're talking about dihedral group. Should you do this operation first and this operation second? Well, I left that interpretation up to you earlier in the semester, but at this point in the course, now that we've discussed permutations, I have to insist that we follow standard conventions, which is that things have to behave with respect to function composition. And remember, function composition, the function on the right is computed first. So you do the reflection first, and then you do the rotation. So if you apply the reflection to k, you negate it. You do the k-fold rotation to it, well, you add k to it. So this operation as a permutation sends the vertex x to the vertex negative x plus k mod n. You might remember from doing these examples with the square earlier in the semester that every time you did one of these operations, you ended up with another reflection. And as we will see, that this bijection we just constructed does in fact have order 2. If you're really crazy, you can actually go through the geometry and figure out, depending on whether n is even or odd, the exact line of symmetry in the polygon this reflection corresponds to. But for the purposes of this course, I'm not going to go that far. It's worth pointing out what happens when you do the rotation first and then the reflection. Well, rotate first says add k to x, then reflect says negate everything. There's a similarity in this formula. They only differ by a minus sign, which tells you that if you rotated by a negative k first, then they would have a plus sign, which tells you that s r to the negative k is equal to r to the k times s, which was an observation I had made previously when talking about symmetries of polygons. My intuitive explanation for that, if you don't actually understand it, is if you're thinking of s as reflection across the x-axis, when you take some kind of rotation operation and you draw it in paint and you reflect it, you're going to get a rotation picture arrow in the opposite direction. And so that sort of tells you go from clockwise to counterclockwise. However, that remark aside, what we have seen is that we have this relationship between the reflection and the powers of the rotation operation. The other thing worth noting is what happens when you square one of these operations. Well, that corresponds to doing it to itself twice. It's given by negative x plus k. Now let's see what happens when you apply this reflection and then the rotation again to negative x plus k. Well, you're going to negate negative x plus k in parentheses, and then you're going to add k to it. No, this is mod n. I'm just leaving that stuff off, but it technically should be there. Distribute the minus sign, and you now have x minus k plus k, which cancels. And lo and behold, you actually have that this element has order 2. So r to the k times s is order 2. And when n is odd, you can prove that it has exactly one fixed point. And when n is even, you can prove it has either no fixed points or exactly 2 fixed points, depending on whether k is odd or even. But we might save those proofs for some other time. In other words, these are actually the reflections, symmetries of the polygons. So in summary, what we can see is that if you multiply 2 of these rotation permutations, it's not too hard to see that the exponents add. Modulo n, of course, because the rotation has order n, so whenever you get something of order n, a multiple of n up here, that's the same as the identity element. If you multiply one of these reflections by rotation, by properties of the reflections, you can replace r to the j with r to the negative j, and then apply this property, and you get this. Similarly, if I multiply a rotation by reflection, I get a reflection. Finally, if I multiply 2 reflections together, you can check that I get a rotation. And so the point behind doing these calculations is that if I multiply any 2 of these permutations in my dihedral group, I get another permutation in my dihedral group. So d sub n is closed under multiplication. Likewise, the inverse of a rotation is also a rotation, and the inverse of any reflection, since it has order 2, is itself. And so I'm also closed under inversion. Ergo, the dihedral group is a subgroup. And that's actually the shortest proof I know to show that the dihedral group is a group, by showing it's a subgroup. So now you don't have to show associativity or any of that other stuff. And in case you wanted to see it, here's another way to write down the multiplication table for the dihedral group of the square. Or that's S. Or not quite. S is this one. As S fixes 0, and you can prove that S also fixes 2. So if you want to actually check the arithmetic, it turns out R times S is the horizontal reflection. R squared times S was the diagonal reflection under this labeling, and R cubed times S is the vertical reflection. So now you get all the reflections we had from before. But as you can tell, computing the table with these relations is actually much, much quicker than actually getting out and doing 64 different pairs of operations. Granted, you might not believe me because I already filled this table in advance, but it only took me 5 minutes. So in conclusion, if you let R be the permutation of the numbers 0 through n minus 1, given by sending I to I plus 1, and you let S be the permutation that sends I to its negative mod n, then this group, consisting of these 2n elements, is a subgroup called the dihedral group of the symmetric group, and it satisfies these relations. The rotation has order n, this negation reflection has order 2, and when you multiply the rotation by S on both sides, you actually get R inverse. And that's actually enough to do all the calculations.